Hello, so today we'll have a second lecture from optics, and as I had mentioned, we will start with lenses. Lenses are made of glass or transparent plastic, and they are one or two edges of them they are curved. So there are two types of lenses: converging lens and diverging lens. So converging lens, it is usually visualized like this. Or simply like this. Diverging lens is visualized like this. Should be usually symmetric. And the image formation by converging lens, so this lens is convex, this is concave. I think there is these words are mixed in your concepts, but here they are right. So image formation by converging lens would be that all the light rays, they go to specific focal point. So focal point is here on the right, and when the light rays they all go through this focal point. This light ray goes straight. This light ray also goes through this focal point. This light ray goes also through this focal point. So you see all the light rays converge to the same focal point on the right. Now when we have diverging lens, and this diverging lens let's make it more nicer. So when we have this diverging lens, we have the focal point on the left, and when there is the light rays, they are coming and they are parallel with optical axis, so they are diverged. So this light ray is diverged to this angle, let's say, and its extension, it goes to this goes through this focal point. When we have this light ray, so it is bent so that its extension goes through the focal point. Now other light rays informative would be here. So the extension of this light ray would go through focal point, and if we had a light ray here, so the extension of this light ray would be here. So now I can make a bit nicer picture for you. So because and this focal point is here on the left. This focal point of converging lens was on the right. So here the extensions of the light rays converge on the left. So here at the same distance would be f of the other side. Here at the same distance would be focal point, another focal point. This would be right, this would be left, this would be right, this would be left. Here it's on the right, here it's on the left, and that's okay with this image. Now with this lens, now image formation by converging lens. So in image formation we have optical axis. This is optical axis. And we have, here would be the center of the lens. So if we have the focal point on the left and on the right, and we have focal point distance to f, this distance is twice this distance at here is twice this distance should be. And we put the object somewhere here between f and 2f. So then the light rays that goes through here, it is bent and goes through here. The light ray that is parallel with the optical axis is bent and goes through the focal point on the right. The light ray that goes through optical center of the lens is not bent. So it is not bent, and it goes like this. It is not bent and it goes like this. So here you see precision is very important. So here you see what happens. We got image by converging these true light rays, so it is real, larger, a bit larger image, and upright. So this is in the case when object is put between first focal point and second focal point. So if it's put somewhere here, then would be different properties right here. If it's put at 2f, then again different. If between here, what we have between 2f and f, what we have now in this example, it is this result. If it's put at f, different result again, and if it's put between the lens and the f, somewhere here, then another result. So there are possible 8 cases, but we are not going to look at all them. But here it is important that light ray that goes that is parallel with optical axis is bent and goes through focal point. Light ray that goes through optical center of the lens, it goes unbent, and here they converge to form an image. Another one, thing that would be important is when object is between f and 2f. So when object is between, now it was is between f and lens, we just had between lens and f. So if f is here, so we put object here between f and lens. So this is our object. So the light ray that goes that is parallel with optical axis goes through focal point. The light ray that goes through the lens center is unbent and it goes straight. And as you can see, what's happening here is that true light rays, real light rays, they don't converge on the right, but they converge on the left. So this should be they converge on the left. So they here, and they form virtual upright enlarged image. So this is image. Virtual upright and enlarged image. So this is how magnifying lens works. That you use to visualize small object. Image is visible because extensions of the light rays produce the image. Now another thing is if we have microscope. So microscope has two lenses, objective and eyepiece. Two lenses, objective and eyepiece. So if we have one lens and it has focal point objective, so this is objective, and the focal point of objective is here. So this is objective, let's call it OB, objective, and microscope is constructed in the way that we put our object a bit further than focal point of the objective. And then the light rays, when they go, so they form an image here, an image here. So this image is so this image is, you can see that it's it should be a bit bigger than this. Here I'm not very good at drawing, but it should be a bit bigger than the object, magnified a bit, inverted and real. Now when we have the second and bigger, this is eyepiece, let's call it EP, eyepiece lens. So this is organized in the way that this would be F eyepiece, and it would be the same here, F eyepiece, and these light rays here, they are not now if we have this kind of image here, we would take light ray that goes parallel with the optical axis. So that one is goes through focal point, and another one that is goes to straight to here, so it goes straight to here. So you can see that they not converge on this side, but what do? So but they would eventually converge on this side. They would made a bit not, this picture is not that, not very nice, but because this is not that straight, so it should converge somewhere here. I think if we have to correct this drawing, it should be, you know, when you don't use, it should be somewhere here, and it should be larger, much larger image. So this is how it should look like. So it should be like this if we used drawing tools. So if we had ruler, then we could if I have ruler, but if I had used, so then it would be a nicer picture. So anyway, you can, you don't need to know to learn on these drawings, but what we get is inverted, magnified, and virtual image. And you see that magnification occurs one time at the objective, another time at the eyepiece. So first image is, so the microscope is constructed in the way that you put objective a bit further than focal point of the objective. You put object further than the focal point of the objective. Then image is formed on the right side, and the eyepiece is positioned in the way that focal point of the eyepiece, that this image by objective would be formed between focal point of the eyepiece and eyepiece itself. So then we, by extending the light rays, we get inverted, magnified virtual image. So this is how it goes. Now it's pretty much, this drawing is pretty much okay. Now the last drawing about the images is that image formation by diverging lens. So image formation by diverging lens looks like we have optical axis, we have diverging lens, we have focal point, and we put the object again between f and 2f. So we put the object, and what's happening now? The light ray comes and it is diverged, so that its extension, so it should be a bit, probably, a bit, 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 a not diverge so much. So it should be diverged like by this amount. Another light ray that goes through the center of the lens is not affected, it is not bent. So the image is formed here. The image is formed here. And because this image is formed by extending of the real light ray, this is virtual. Again, this is virtual light ray. This is virtual light ray. So this image is image, this is object. So it is upright, virtual, and what is it? Smaller than the object. Okay, and this point there is F again. So this is how it goes. Okay, now there's a lot of drawing in these lectures. Now the human eye. So the human eye, it is, now I will use, maybe not draw this human eye because I'm not that good at drawing. You see that this human eye consists of, it is oval shaped. It has the main things that are here, there are that the human eye has two lenses. One lens is this cornea here. Cornea is a lens. It has fixed focal length, and there is this another lens is called just lens, and it has variable focal length. They are both converging lenses. This is also filled with aqueous humor that is also converging, and when light goes through all of these structures, it gets converged, and the converging properties of the lens, they are changed by ciliary muscles that are here. The ciliary muscles attached to this lens by suspensory ligaments, and when light rays go through these lenses, they are converged, and the image is focused on the retina, and receptors are you will learn later that receptors, that the signal is transmitted through receptors to optical nerve and then to the neurosensory cortex. So what is another thing important, that these converging properties of the lens, that it can be less converging or more converging, is called accommodation of lens. So during biophysics in later years, you will know more about this image processing by human eye. So now it would be, so far we've been dealing with optics that is based on geometry, on geometrical optics so far. Now we will deal with what's called physical optics. So physical optics explains phenomena like polarization, like interference, and diffraction. So all these three phenomena. So polarization is a property of transverse waves, and it specifies the direction of the plane that contains the oscillation relative to the direction of propagation. So this is the definition, is how to understand this definition, is that electromagnetic wave consists of magnetic and electric fields. So this is called the electromagnetic field. So and electric field. So these fields, they are oscillating and they are perpendicular to each other. So what happens is that, so electric field and magnetic field, so they are oscillating and they are perpendicular to each other. So now how to better illustrate this polarization. So again, polarization of light. So okay, so now as we can see, the electric field is oscillating here, and magnetic field and is in right degree angle, is at the right angle with the magnetic field. So okay, so we have electric field and we have magnetic field here, and we have right angle. So maybe let's write this angle in pencil. So you see I'm drawing a cross section here. You see that we have electric field and we have magnetic field. So in this my example, I have drawn like this. This is electric field and this is magnetic field. So we may stick to that representation, that here it is electric field, here it is magnetic field. So here B, here E. Sorry, here it is magnetic field, here it is electric field, and they are at a 90-degree angle. So here they are the same. If I'm showing the cross section of this wave, so here you can see that it is electric field. So here the same vector, and here would be magnetic field vector here. And they are at the right degree angle. So right degree angle. What is interesting, so this would be cross-sectional representation. So what is interesting, it would be that when light, this is one ray, let's imagine one ray. When light comes, it comes in many rays. When light comes, so there can be another one ray is coming here, but there can be or wave, let's say ray or wave. So when the beam of light comes, there are a lot of waves like this, and the electric field, another one electric field, can be orientated to this one, like in this direction. So this is E field, another one, and it can be, so B field is at the right angle, but B field is like here, you see. So B field is like here, and they have the right degree angle between each other, but you see the direction of E field changes. And there can be also another one electric field, that would be positioned here, and there can be B field that it is positioned at the right degree angle, so it would be positioned somewhere here. So you see what's happening. That there are, in a light beam, there are a lot of waves. So when we have a light ray, so a light beam, so then electric field would be like this one of one wave, of another one it would be like this, of another one it would be like this, like this, like this, and like this. So there are a lot of orientations of these electric fields because there are multiple waves coming, So we're not showing magnetic field, we're showing just electric field. So because there are multiple waves coming, so if we allow to pass only a light wave, electromagnetic wave, or a light wave that is oriented only at one particular direction, electric field that is oriented only at one particular direction, of course there would be magnetic field oriented to this electric field at the right degree angle. But if we allow to pass only for one orientation, so let's say we would allow to pass this one, so then this would be polarized wave, that it contains only electric field oriented at some particular direction. So if we have in unpolarized light, we would have electric field. So unpolarized light, so electric field is oriented at different directions. In polarized light, it can be oriented only at this direction, only at this direction, so the direction that we choose, but there's always only one direction. Always only one direction. There's no multiple directions. There's only one direction. So this is called polarized light, and it's used in polarized glasses to reduce glare. But basically, this polarized light has very in lasers it is used. We will discuss a bit later this thing. Now another thing, it is called wave interference. So wave interference, as we were talking with mechanical waves, so there are two types of interference. So one is constructive interference, when maxima, the points of maxima and minima, they correspond to each other, and we obtain a much, and these waves, they add up, and we obtain a much when we add two maxima, we obtain twice higher amplitude, and in minima we obtain twice lower amplitude. And here again, these two maxima, they add up, these two minima, they add up. So this is called constructive interference. And another one is destructive. So in destructive interference, when there is maximum of one wave, there is minimum of another wave. So, and after we sum these two, we get 0. This cancels out this cancels out this, and this cancels out this, So amplitude is 0. If we have some intermediate variation, so we get something in the partial interference. So we get something between this and this. If maxima and minima, they in this case they correspond, here they don't correspond, but if we get something within this corresponding, so then we get partial interference, with the result would be intermediate between this and this. Now wave diffraction. Diffraction of wave. So diffraction of wave is spreading of a wave as the wave passes narrow opening. So when the wave comes to this opening, so then it is spreads through this opening. So it is spreading of a wave as it passes through a narrow opening. It occurs with sound waves, with water waves, as they go around obstacles. When we have light waves, imagine we have two narrow gaps. So there is one light beam coming and another one light beam coming. Two light waves coming. And this is spread, and this also is spread. So they spread, and if we have a screen here, what do we get? This is a screen. And it seems that we get the view that looks like this. Here it is dark, here it is white, here it is dark, here it is white, here it is dark, here it is white, and here it is dark. So this is dark, this is white. So what is this? This is so when we have dark, it is interference minimum. When there is white, there is interference maximum. So because when there are two waves, again here like this in this picture, there occurs diffraction. Here occurs diffraction, it goes through the wave spreads through the narrow opening, diffraction plus interference. So it means that we have interference we can write here that we have here we have interference minima of diffraction, and here we have interference maxima of diffraction. So of course it is the same and here, and this black here also. So why do these happen? So you can see that when the light goes through the narrow opening, so the light beams go through these two narrow openings, so we have light waves, and when they are in phase, so they correspond, you see that these oscillations, they correspond, maximum is corresponding with maximum is corresponding with maximum, minimum with minimum. So this is constructive interference, and we see bright view when we have another thing we have this would converge, see, like this. So these two waves would converge, and they would form destructive interference. Destructive interference would be dark spot on the screen. So because maximum with another maximum, they don't correspond. Maximum is here, and it corresponds with minimum of another wave here. Minimum of the first wave corresponds with maximum of another wave. So in the end, they cancel each other out. So we see dark spot, and we see, on this case, we see bright spot. So this occurs due to diffraction and interference, but sometimes it's called diffraction pattern. So, but they both occur. And the last thing that I wanted to tell you is that when the light goes through a hole, what's happening? When we have a hole, when a laser goes through a hole, to a small hole, we see white and dark bands. Why do we see this? Because of diffraction and interference, as I told you just now. So we see white and dark bands, so laser passing through a pinhole. So this is due to diffraction, sometimes just diffraction term used, but due to diffraction plus interference. When laser is passing through small hole, so the same thing is happening here. Here is just cylindrical opening, cylindrical hole, and the resolving power resolving power is the ability to distinguish two objects as two. So when we have, let's say, two holes, two pinholes or some kind of objects, when the light shines on them, we see if these objects are small, very small, so when the light shines on them, we would see this view, this kind of view. Due to diffraction, very small objects, if we see with microscope, we were looking with microscope or something, or if these just were two pinholes that were lit by a laser, so, and we would take a closer look, we would see this. So here we can distinguish that there are two objects. We can distinguish. In another picture, when these objects are closer to each other, so we can, the diffraction pattern, the diffraction does its job, and these objects, they merge a bit. The objects, they don't merge, but due to diffraction, it looks like they merge a bit. So because of this, it is difficult to, so two objects, so barely, so it is two objects, and in this case they are resolved as two. In this case they are barely resolved because they became closer to the closer distance. And when these two objects come to even closer distance, so then it's practically impossible to resolve and to visualize this object as being two objects because of the diffraction. So imagine these two objects can be some kind of very small samples. If you're looking using some kind of microscope, or if you're looking at at laser passing through two pinholes, and you would magnify this pattern a bit. So here, because the distance between these two objects became very small, they are unresolved as two objects. So diffraction reduces the resolving power of optical devices, so it is impossible to visualize the closely spaced objects. And because we see just concentric bright and dark images, so it reduces the resolving power of optical devices used in research. So this lecture is finished, and thank you for listening.